Hello everyone, welcome to Canal Physics. Today's video will be on propagation of uncertainties. Before we start today's video, don't forget to buy your copy of Physics Foundations. Please click the link in the description below. As the author, I guarantee this is the perfect resource for mastering the fundamentals in physics. Ideal for a Year 10 or 11 student who wants to build confidence and improve results in ATAR physics. Now let's start today's topic. Before we learn how to propagate uncertainties, it's important to know how to quote them properly. So here are some dot points to help us. Uncertainties must only be quoted to one significant figure. This goes for all three formats: absolute, fractional or relative, and percentage. However, if the first digit is 1 or 2, then two significant figures is acceptable for greater clarity. But 3 or more significant figures is generally not acceptable for uncertainties, because we can't be too certain about our uncertainties, pun intended. But another rule to consider is that the number of decimal places in the result and its absolute uncertainty must match. So to highlight the first three dot points, I've put a table here of some acceptable ways to quote uncertainties. So for the absolute column, I've just put units for context. And here I've got fractional uncertainties and percentage uncertainties. So you can see that in all these columns, all these examples, that if the first digit is not a 1 or a 2, then only one significant figure is acceptable for the uncertainty. But if it's a 1 or a 2 for the first digit, doesn't matter where it is in place value, then a second significant figure is acceptable for greater clarity. Introducing the first propagation rule for uncertainties. When adding or subtracting, add the absolute uncertainties to get the uncertainty in the result. So what does this look like? Well, let's try these examples. So if A equals 2.01 plus or minus 0.17 and B equals 8.3 plus or minus 0.6, we can calculate A plus B with its uncertainty. So first let's just find A plus B, and this is going to be 2.01 plus 8.3, and that's just going to give us 10.31. And the uncertainty in this number, which we'll denote like this, since we're adding numbers, we must also add the absolute uncertainties. So that becomes 0.17 plus 0.6, and this equals 0.77. So writing this in full, the number with its uncertainty, 10.31 plus or minus 0.77. So this can't be written as our final answer because we have two significant figures for the uncertainty, and this first digit here is not a 1 or a 2. So we can round to adhere to this. So therefore, our uncertainty must be 0.8. But now this means there's one decimal place in the uncertainty. And remember that the uncertainty decimal places must equal the decimal places in the value. So we round 10.31 to 10.3. So one sig fig for the uncertainty, and the number of decimal places are equal. So that is correct. Now let's try the subtraction. So B minus A, that's going to be 8.3 subtract 2.01, and this equals 6.29. Now the uncertainty in this, so even though we subtracted the values, we still must add the uncertainties. So just like before. And again, that's going to be 0.77. So writing this out, we have 6.29 plus or minus 0.77. And again, we have the same problem here. We have two significant figures for the uncertainty, and the first digit's not a 1 or a 2. So we must round that to 0.8 again. And one decimal place in the uncertainty means one decimal place for the final answer as well. So we round that to 6.3. And that's it. So just a final note here, it's important you see that we always increase the uncertainty as we propagate. It doesn't matter what the operation is, because the more you use uncertain values, the more uncertain you're going to get in your final answer. Now for the next propagation rule. When we multiply or divide, we add the percentage or fractional uncertainties to get the uncertainty in the result. So to see how this works, we've got a rectangle here, and we're going to calculate the perimeter and area. For the sake of comparison, I'm going to calculate the perimeter and area so you can look at how the addition and subtraction rule compares to this multiplication and division rule. So calculating the perimeter of this rectangle, we simply add the side lengths, and this equals... So now to calculate the uncertainty in the perimeter, we simply add the uncertainties for all the side lengths, and this equals... So writing this as a final answer, we have 15.8 plus or minus 3.4, and both are in centimeters. But since the first digit is not a 1 or a 2, we must round this uncertainty to one significant figure, and that will dictate the number of decimal places in the perimeter. So calculating the perimeter with its uncertainty, that was just a quick recap of the previous rule for addition and subtraction. Now let's actually do the multiplication and division rule by calculating the area. So let's just go ahead and calculate the area of this rectangle, not considering the uncertainties. And that's just going to be length times width. So I'm going to assign this 3.2 as the width and the 4.7 as the length. Doesn't matter which way I do it. And this gives us 15.04 square centimeters. So now I'm going to show you two methods to calculate the uncertainty in this area value. Method 1, I'm going to add the percentage uncertainties in length and width. Method 2, I'm going to add the fractional uncertainties in length and width. They're going to give the same answer, but I'm just going to show you both methods so you can choose your preference. So first, to start method 1, I multiplied length and width to get the area. And by this rule, this dot point here on the top, I must add the percentage uncertainties in length and width, and that will give me the percentage uncertainty in the area. So the percentage uncertainty in length is equal to 1.2 divided by 4.7 as a percentage. So that gives me 25.5 etc. percent. And the percentage uncertainty in width is equal to 15.6 etc. percent. So now that I've got my percentage uncertainties in length and width, I simply add them to get the percentage uncertainty in area. So that gives 41.1 etc. percent. So remember, I'm not rounding until the very end. So this 41.1% is the percentage uncertainty in 15.04 square centimeters, the area. So to get the absolute uncertainty, or just the uncertainty in area, that's simply 41.1%, etc., etc., of 15.04, the actual area. And that will give me 6.19 square centimeters. Now, before writing the final answer, I just want to show you another way to get this uncertainty, 6.19 square centimeters, but we're going to add the fractional or relative uncertainties. Now, keeping in mind this is pretty much the same thing as adding the percentage uncertainties in method 1, it's just that I'm not using that 100% in each step because it actually ends up cancelling out anyway. So the relative uncertainty in area equals the relative uncertainty in length plus the relative uncertainty in width. And substituting all the values, I get... And now rearranging for the uncertainty in area, I simply multiply the 15.04 across, which gives me... And this, as you might expect, equals 6.19 square centimeters. So this top line here makes it clear why method 1 and 2 give you the same answer. Because if I multiply all of these terms, these fractions, by 100%, that is adding the percentage uncertainties to get the percentage uncertainty in area. But since that 100 is common in each term, that just ends up cancelling out anyway. So method 2 is my preferred method because there is less work to do. So now we can write our final answer. So writing area with its uncertainty, we get this. But of course, this is not acceptable because 6.19 is 3 significant figures. So we need to round that to one significant figure. And that's going to leave us with 6. But then that means there's no decimal places in the uncertainty, so there must also be no decimal places in area. So our final answer is 15 plus or minus 6. And those are both in square centimeters. And that's it. So what happens when we multiply a number with an uncertainty by a coefficient, such that the coefficient itself does not have an uncertainty, it's simply a scale factor? So when multiplying by a coefficient, the absolute uncertainty also gets multiplied by that coefficient. So put simply, if you double a number with an uncertainty, the uncertainty also gets doubled, or tripled, quadrupled, whatever the factor is. So for example, we're going to consider a circle of radius 5.80 plus or minus 0.25 millimeters, and we're asked to calculate the circumference. So let's just start by writing out the radius. And the formula for the circumference of a circle is 2 pi r. So ignoring the uncertainty, let's just calculate the circumference. And this is 36.44, etc. in millimeters. So we haven't done anything with uncertainties yet. So what about the uncertainty in the circumference? Well, since the circumference is simply the radius multiplied by two coefficients or two constants, 2 and pi, the uncertainty in the circumference is simply the uncertainty in the radius multiplied by these constants, as the dot point above suggests. So writing this out is 2 pi times the uncertainty in radius. So whatever numbers you multiply the radius by, it's the same deal for the uncertainty. So substituting our value for the uncertainty in the radius gives, and this equals 1.57, etc. millimeters. So writing the circumference with its uncertainty is, but there are three significant figures in the uncertainty, but keeping in mind the first digit is a 1, so it is acceptable to go to two significant figures for more clarity, because 1 is quite a small number. So rounding to two significant figures will give us 1.6 for the uncertainty, and that means one decimal place for the uncertainty, so that dictates the number of decimal places in the circumference itself. So our final answer is, and those are both in millimeters. And that's the answer. So what about dividing by a coefficient? Well, it's very similar to multiplying. So when dividing by a coefficient, the absolute uncertainty also gets divided by the coefficient. So in this example, we're going to contrast two different ways to measure the period of a pendulum. We discussed this in a previous video, but just a reminder, the period of a pendulum is simply the time it takes for the pendulum to complete one swing, and that is a there and back to the original position swing. So I'll just read out the example. Show that the timing for 10 swings, which is shown on the right here, is a more precise method to determine the period of a pendulum compared to timing just one swing, which is shown on the left. So on the left here, we have 1.3 seconds. This is pretty similar to my 100-meter sprint time. So the scientists release the pendulum here, and that's when they press start. They let it swing once, there and back, and press stop when it returned to the original position. So on the right here, we've got 12.4 seconds. So the scientist released the pendulum here, and that's one swing, 2, 3, etc., and waited for 10 swings and pressed stop. So as expected for the same pendulum, this time here on the right is roughly 10 times more than the one swing time. So the time on the left here is directly the period, and I'm going to use capital T for period as we typically do in physics. Now taking note that this is a digital stopwatch, so the uncertainty is the smallest reading, which is 0.1 because it goes to one decimal place. So the smallest possible reading is 0.1 seconds on this timer. So writing out the period, we get, and both period and its uncertainty are in seconds. So a good measure for precision is the relative or percentage uncertainty, because that tells you how big or small the uncertainty is relative to the quantity. So the smaller the percentage uncertainty, the higher the precision. So that's how we're going to compare the precision of these two measurements, is calculate their percentage uncertainties. So the percentage uncertainty in this measurement of period is 0.1 over 1.3 multiplied by 100%, and that equals, and to the nearest whole number we got 7%, keeping in mind we must only have one significant figure for uncertainties, because this is an uncertainty not starting with 1 or 2, so one significant figure is appropriate. So for the time for 10 swings of the pendulum, I'm going to use lowercase t just to represent time in general, but with a subscript 10. And reading this from the timer, we get the uncertainty is the same as before because it's the same timer. It goes to 1 decimal place. So to get the period from this measurement, we would divide this by 10 to get the average time for one swing amongst these 10 swings. So we're going to divide both the quantity, the time measurement, and its uncertainty by 10, which gives us... So this is the point where we use the dot point rule above. So we get... So before even calculating this percentage uncertainty, you're already seeing that this measurement for period is a lot more precise than the timer on the left. Because if we just focus on the range, in the first period measurement for one swing, the measured period is anywhere between 1.2 and 1.4 because it's 1.3 plus or minus 0.1. But for the period calculated from this measurement on the right, the range of values is much smaller, or you could say more precise. In other words, this is only from 1.23 to 1.25 because it's 1.24 plus or minus 0.01. And this is all because of this dividing by a coefficient rule. The quantity and the uncertainty get divided by the factor. So let's finish this by calculating the percentage uncertainty in this period value. And rounding to one significant figure, this is 0.8%. So we can see this percentage uncertainty is much smaller, roughly 10 times smaller than the original percentage uncertainty, therefore more precise. The last rule for today is concerned with raising to a power. When raising to a power, the percentage or fractional uncertainty gets multiplied by the power. To show this rule in action, we're going to calculate the area of one face and the volume of a cube. And this cube has a side length of 1.0 plus or minus 0.2 centimeters. So I'm going to use a lowercase l to show the length of the cube. The area of one face, that's just going to be the area of a square, which is L squared, and this gives us 1.0 square centimeters. So first I'm going to find the percentage uncertainty in the length, and this equals 20%. Now to get the percentage uncertainty in the area, we look at the dot point rule. We need to look at what power L was raised to get A, and that power is what the percentage uncertainty in length will be multiplied by to get the percentage uncertainty in area. So this gives us 40%. So since 40% is the percentage uncertainty in area, the uncertainty in area is 0.4 times the area. And 1 is a nice easy number to work with, so it's 0.4 square centimeters. So writing out the full answer gives us, and that's the area with its uncertainty. Now to calculate the volume, this will simply be the side length cubed. So substituting to get the volume is nice and easy again because we're just working with 1. So this is going to be 1.0 cubic centimeters. Now to get the uncertainty in volume, well, the percentage uncertainty in the length will be multiplied by 3 to get the percentage uncertainty in volume. So this gives us 60%. So you can see how this is greater than the percentage uncertainty for area because the power is greater. So 60% of the volume will give us the uncertainty in volume, and this will give us 0.6 cubic centimeters. So writing the volume with its uncertainty to give our final answer, and that's that. Thank you for watching this video. If you found it helpful, please like and share it, and subscribe to my channel for more. Also, click the link in the description below to buy your copy of Physics Foundations. As the author, I guarantee this is the perfect resource for mastering the fundamentals in physics. Ideal for a Year 10 or 11 student who wants to build confidence and improve results in ATAR physics. Thank you.